done something wrong in this computation. So I guess my advice to you is make sure you write the thing out completely and then solve it correctly. Try not to take shortcuts. That might get you into trouble. Now, you've got to be careful when you're talking about solutions if you're talking about individual species. So, let's say we have 0.1 molar sodium chloride. And maybe the question is asking you, what is the concentration of the sodium ion? Because what does sodium chloride do when it gets into water? First thing it does is it dissolves. The second thing it does is it dissociates. It breaks up into sodium ions and chloride ions. So, if I have a 0.1 molar solution of sodium chloride, this would imply that I have a 0.1 molar sodium ion concentration, because I'm getting one sodium ion for every sodium chloride. I'm also getting one chloride ion for every sodium chloride, so I have a 0.10 molar chloride ion concentration. Let's contrast that with this problem. Suppose I have a 0.10 molar magnesium chloride solution. I put the magnesium chloride into water, it dissolves and dissociates, and so it breaks apart, and I get 0.10 molar magnesium ion. But here's the difference. How many chlorides am I getting for each one magnesium? 2. So the concentration of the chloride ion is going to be twice as much. It's going to be 0.20 moles per liter for the chloride. And if I had a different formula where there were 3 atom components, then it would be 3 times that amount in the sample. Trouble?
And I'm just going to throw some numbers out there for you. But what if you have 0.10 moles of H2O? You have 0.10 moles of H2 or just H?
Well, first of all, in H2O, it's probably not going to break down.
Right, of course. Okay.
So it would stay as a single unit, and so the best I could say is I had 0.10 moles of H2O.
Okay.
So you want to pick a different substance to make your point?
Yeah, anything with the...
How about aluminum chloride?
Yeah, there we go.
Can you tell me the concentration of aluminum ions?
I could probably tell you, given what you've given us earlier, 0.10 moles.
Well, what you're saying is correct, but you're not answering my question. I asked you for the concentration of the aluminum ion. And the answer you gave me was a mole value. Is a mole value a concentration? No. A concentration is a mole per liter. So the mole value alone doesn't tell me the concentration. What do I need here in order to be able to answer my question, what the concentration is? I need to know the volume. You gave me 0.1 mole of aluminum chloride. Is it in a particular volume of solution? It's your problem.
I mean, why don't we just throw you a number?
Sure.
Okay. Let's go ahead and borrow the one from over there, 0.05.
All right. So we're putting this in 0.05 liters of solution. So can we get the molarity of the aluminum chloride?
I'm sure given that we could, yeah.
What would it be? Or how would we get it?
We would
Take the moles of aluminum chloride
And divide it by the
and divide it by
solution.
the volume. Okay. So that's going to be 0.10 moles divided by 0.050 liters molar aluminum chloride.
Okay, so what are those values, those numbers over there mean?
These numbers?
Yeah, what does all that mean?
Those are concentration.
Okay,
So that's the equivalent of what this is in your problem.
okay.
Okay?
Well, what I mean is the arrow pointing to all the cations and anions, what do those mean as well?
I'm separating out the individual species.
Okay.
So in other words, when I make this up, I'm going to go to the balance and I'm going to weigh out whatever the gram amount is to give me 0.1 moles of aluminum chloride. And I'm going to put that into a piece of volumetric equipment, probably a flask that looks like this, that is 50 milliliters and has a calibration point somewhere in the neck of the flask.
All right.
So I'm going to put that solid aluminum chloride into that flask. And I'm going to add water until my meniscus reaches that line, so that I know I have exactly the 50 milliliters of the solution. And then the question becomes, what's the concentration of that solution? Concentration is in moles per liter, so I take the moles of aluminum chloride divided by the volume
Yeah, I understand that
gave
part.
me, and I get this. Okay, now, when I do that, when I put the water into that flask, what does the aluminum chloride do? It dissolves. That's right, but it does one more thing beyond that. Since it's an ionic material, it not only dissolves, it dissociates. It breaks apart. And it breaks apart into its components. And its components are the aluminum ion and the chloride ion. Now, if I have 2 moles per liter of aluminum chloride, when that breaks apart, how many aluminum particles will I have in a liter? Because what this tells me is I have 2 moles of aluminum chloride in that 1 liter sample.
Okay, total.
Total.
Okay.
If I have a liter.
All right.
Okay, so if I have a liter, I have 2 moles of aluminum chloride. When that breaks apart, how much aluminum will I get?
I don't know.
What does aluminum chloride break down into? Aluminum and
Sure.
chloride. How much aluminum? Well, look at the formula. The formula tells me that if I have 1 aluminum chloride, I can expect to get 1 aluminum. If I have 2 moles of aluminum chloride, I could expect to get 2
2.
moles of aluminum. So in that same liter, where I have 2 moles of aluminum chloride and it breaks down, I would get 2 moles of aluminum. I'm still in the liter,
Okay.
so its concentration is going to be 2 molar aluminum ion.
Okay.
But now, what about the chloride?
You have to double that because.
Double it?
Oh, sorry, triple.
Triple it. Because when 1 aluminum chloride breaks down, I get 3 chlorides. So the amount of chlorides is going to be 3 times the amount of what the aluminum was.
Makes sense.
And so if you're asked for individual chemical species, you have to take into account that dissociation. Okay, so let's assume that I have a small beaker that contains some, we'll just play with salt, sodium chloride, NaCl. And I'm going to give you some information about that solution. I'm going to tell you its molarity. Its molarity is what I'll call M1. And I'll tell you something about its volume. Its volume is V1. Now, if you knew those numbers, if you knew the molarity and you knew the volume, and I asked you for the moles of NaCl, could you calculate it? How would you get it? What would it be? I'm sorry? So it would be molarity times the volume. Because if I look at my original molarity formula, it's moles over volume. So if I'm trying to calculate the moles, solving that mathematically, I would have molarity times the volume should be equal to the moles. Okay. distilled water, have I changed the volume? No? Yes. I'll give you the new volume, V2. Have I changed the concentration?
Yes. No.
Yeah, I have. If I put a bunch of water in there, I am changing that
Diluting it.
concentration. So I'll give you the new concentration, M2. Now, if you knew these values, could you tell me how many moles of salt are in the large beaker? Vote a B. M2, V2. Now, in going from the small beaker to the large beaker, did I lose any salt? No. All the stuff that was in the small beaker ended up in the large beaker. Did I gain any salt?
No.
No. The only thing I added was water. So what can we say about moles of salt in the small beaker and moles of salt in the large beaker?
They're the same.
They have to be the same. So, what I've done is I have derived a formula that can be used for what's called dilution problems. And dilution problems are common. In our laboratories, we buy chemicals from the Acme Chemical Company. And when we buy those chemicals, let's say we're buying an acid or a salt solution or whatever, we typically buy only the strongest concentration, what's called the saturated solution. So hydrochloric acid, we buy 12 molar hydrochloric acid. That's as concentrated as it comes. But yet we use lots of other concentrations in our lab experiments. You'll use 1 molar HCl, 0.1 molar HCl, 0.4 molar HCl, 6 molar HCl. Why do we only buy the 12 molar? Exactly. If we bought the other concentrations, we'd be paying a lot of freight on water. We have our own still in the lab to make distilled water, so we can always add water and make whatever lower concentration we want to. So it's critical that we know what the dilution formula is so that we can make those weaker solutions. I think this is something you'll probably do in the laboratory. You probably have had or will have an experiment. Have you done a titration experiment yet?
Yes.
Where you made up a sodium hydroxide solution?
Yes.
And then they have you actually measure out some sodium hydroxide and use this formula to determine how to make up that solution. So let's take a typical example. If we have 3 molar NaOH and we want 500 milliliters of 10th molar NaOH, how would we make up that solution? This is a typical dilution problem. Now, when you read these problems on the exam or in the laboratory, sometimes it gives you a big hint and says, how much do I have to dilute it to? Or if I dilute it by such and such an amount or whatever. And when you see the word dilute in the problem itself, there's a physical trigger that tells you, aha, this should be a dilution type problem. That's not always the case. In this case it says, I have 3 molar NaOH, I want 500 milliliters of 0.1 molar NaOH. Not a word about dilution in the problem. But think about it logically. If I have 3 molar NaOH and I want to go to 0.1, what do I have to do? I have to add water, and if I add water, I am diluting the solution. So as quickly as I can, I want to arrive at the conclusion that here is a dilution problem. Now my suggestion in working these problems is on your scratch paper or in the margin of the problem, make a little table. M1, V1, M2, V2. And go through the problem and try to fill in this table. So I would read 3 molar NaOH. 3 molar, is that a concentration or a volume? It's concentration. Is it M1 or M2? Or does it matter? Doesn't really matter. The 1s and 2 are just labels. I could make it either one that I wanted to. Since it's the first one I came to, I'm going to call it M1. Okay, continuing on. I want 500 milliliters. Okay, is that a concentration? concentration or a volume?
Volume.
The volume. Is it V1 or V2? Or does it matter? It does matter this time. And in fact, it is V2. Because it's not associated with the 3 molar. If you keep reading, it's 500 milliliters of the 0.1 molar. So it's got to be V2. So my V2 is 500 milliliters. Of 0.1 molar, is that a concentration or a volume?
Concentration.
So is it M2 or M2?
M2.
Must be M2. One's already taken. So this is 0.10 molar. So is it clear in my mind what it is that I'm missing and what I'm looking for?
Yes.
So I want V1. Can I come back over to my dilution formula here and solve this mathematically for V1? Sure. V1 is equal to M2 V2 over M1. Can I go back to my table on my scratch paper or margin and plug those numbers into this formula? M2 is 0.10 molar, V2 500 milliliters, M1 3 molar. What happens to the molars here? They're going to cancel. And what am I left with? I'm left with the volume term. Do I have to change that 500 milliliters to liters? I don't have to, as long as I'm willing to say that if I leave it as milliliters, my answer will be in milliliters. If I change it to liters, my answer will be in liters. So the units allow me to use either one here in this particular case. And so I do the math, 0.5 divided by 3. So y1 is equal to 0.127. Did I do that wrong? Yeah. 6, 7? No. No, I think it's 17, is it?
It is.
50 divided by 3. 17. So about 17 milliliters. 16.6. So what is this telling me? That if this is what I want to do in the laboratory, and I think this might be what you did in the lab, isn't it?
Yes.
And then you calculated that you needed 17 milliliters of stuff to make this happen. And what is it telling you? Take 17 milliliters of the 3 molar NaOH and add, we're going to add water. How much water? You sure? The 500 should be the total. So I would subtract 17 from the 500. I would have added 483. But is that going to be perfect?
No.
Turns out no. There's a problem with that. Here, if you have 50 milliliters of water and 50 milliliters of alcohol, what's the total volume of the solution? It turns out to be about 95 milliliters. It's because the two particles can get closer to each other than the individual molecules can to themselves. A nice example of this would be if I had a beaker, a glass beaker in here, and I filled it totally with marbles so that I couldn't get another marble in there. Could I then add some sand to that beaker? And the sand would trickle down in. Why? Because the sand will fit into the spaces between the marbles where the marbles won't fit. And so that's what happens when you add different substances together, is that their volumes, we say the volumes are not always additive. So we need to be very careful when we do this type of thing. And just because we added 17 milliliters of the NaOH and 483 milliliters of water doesn't mean we're going to get exactly 500 milliliters. Although in this case we'll be very close, because we're dealing mostly with water solution. Yes, ma'am?
So
concerned about it, what I would do is I would find one of those volumetric flasks that was calibrated for 500 milliliters. And I would take my 17 milliliters of the NaOH, put it in here, and then I would add water probably to here to start with. I would shake it up very thoroughly so that that got mixed, and then I would add whatever water I needed to get back to the line in the neck. And then I'm pretty certain that I have exactly 500 milliliters of solution. Now, I don't think we have to be that careful in our laboratory preparations, especially if we go on and standardize the sodium hydroxide solution. That's what we typically do in a titration. We standardize it by doing the titration to find out what the actual concentration is. And we'll take a look at that. So, any questions on dilutions? Sure. Okay, so if we have a kitty chem lab that requires 6 liters of 4 molar HCl, I think I mentioned we only buy 12 molar HCl, so how would you make that up? If you're the lab tech person, how are you going to make that up that solution for us?
What did I do here?
Okay, let's go through it. 6 liters, volume or concentration?
Volume.
V1, V2, doesn't matter.
I did
All
too.
right, we'll call it V1 because it's the first one I came to. 6 liters of 4 molar, concentration or volume?
Concentration.
M1 or M2? Doesn't
One.
matter.
One.
Yep, gotta be M1. We have 12 molar HCl. M2. So I'm looking for V2. So M1 V1 is equal to M2 V2. So V2 must be equal to M1 V1 over M2. Can I put in the numbers?
Yes.
M1 is 4 molar. V1 is 6 liters. 12 molar. So it looks like 2 liters. problem, but it went away.
Well, I did mine with the, I used Zero, like you did in the first problem. Not problem, not really. Where, later resolve is what we want to do.
Did you get the right answer? Were your concentrations different? Was my M1 your M2? Yeah, you're okay. It's 12.0. Decimal point makes a big difference. Sorry. Try to make them bigger next time. Other questions? All right, great. Can we complicate the issue?
Of
Chemistry is
course.
famous for is taking simple issues and making them more complicated. We can complicate this particular issue by saying, look, maybe we can combine some concepts that we've done. Now, earlier we looked at stoichiometry, and now we have this concentration business. Maybe we can put the two together into one problem. So, here's a problem for us to consider. Let's see how we would do it. Okay, good. You got it written down? So, a 50 milliliter sample of 0.025 molar silver nitrate is mixed with 0.0400 molar chromium-3 chloride. Whew, there's a mouthful. What is the minimum volume of chromium-3 chloride required to completely precipitate the silver chloride? Okay, let's talk about this. Required to completely precipitate the silver chloride. How am I going to determine that? That sounds like a stoichiometry problem, a limiting reagent problem. I have to work that in terms of what? Moles. So, what's the first thing I need here in order to get this thing started? A who? Volume? Volume? Yeah, that'd be the answer. If we could get that right away, that'd be great. I think we're going to need some other stuff to help us. I think we need an overall view of what's happening.
A balanced equation?
A balanced equation. We need a balanced equation. So what's reacting with what? Silver nitrate. Oh my God, look at this. They're giving us the name and expecting us to know the formula. So do we know the formula for silver nitrate? And what is it? And so? I'm getting a lot of positive feedback. That's it. Okay. We're going with it. Wow, what am I reacting that with? Chromium-3 chloride. Okay, I need a formula for chromium-3 chloride. CrCl? 3? We agree? Okay. Reaction occurs. Waka, waka, waka. What do I make? It's a type of metathesis reaction. I'm switching the partners. So, silver must be combining with
Chlorine
chlorine. Silver's a, what charge?
plus 2. Wait, no plus.
Plus 1. Chloride? -1, correct
Negative 1.
formula? Chromium, what's the charge? Can't tell by looking at the periodic table. It's a +3 because it's telling me +3 in the chromium 3 chloride. The 3 means charge on the metal
Three.
ion. So chromium is a +3 charge on a nitrate. -1, correct formula. I think this is what I heard. I'm hoping this is what I heard. I'm praying this is what I heard. Okay, so I've got correct chemical formulas. What's my next step? Balance that sucker. Is it balanced? Maybe we got lucky. Here? We're good. Balanced chemical equation. I'm well on my way. All right, what's the minimum volume of chromium 3 chloride required to completely precipitate silver chloride? Well, in order for me to answer that, don't I need to know how much silver chloride I have? And I need to know it in moles. So, what do I know about the silver nitrate? I have 50 milliliters of a 0.0250 molar silver nitrate sample. Can I take that volume and that concentration and change it into moles? That's exactly what I need to do. So the first thing I need to do is to say, okay, I have 0.0250 molar, which is a mole per liter. It often helps unit-wise to take that capital M and write it in terms of its significance, the mole per liter. And then I'm going to multiply that by the volume, but in this case, can I leave it in milliliters? No, I have to use liters. So this is a 0.050 liter sample. So that should give me the moles of silver nitrate. Somebody got that? Showing? Sometime. Not even close. Must be Monday. 0.0125 moles, is that better? 2 zeros. There were 2 zeros. Just one on the wrong side. Okay, is that better? Good. Just seeing if you were paying attention. Making sure we got that. Now what do we do? Well, we want to know something about the chromium 3 chloride. So, can I relate this mole amount of silver nitrate to the chromium chloride? Stoichiometry problem, right? So if I have 0.00125 moles of silver nitrate, then I'm looking for moles of the chromium chloride compared to the moles of the silver nitrate. And where do I get those numbers from, and what are they?
The balanced equation.
Balanced equation.
And it's 1, 2, 3.
1 to 3. So moles of silver nitrate cancel. So it looks like I'm left with 0.00042 moles of chromium chloride. So what's that telling me? That's how much chromium chloride it would take to totally precipitate my silver nitrate, and convert the silver into silver chloride. But it's asking me for a volume, and I've got moles. So now, can I use my molarity relationship? Remember that molarity is equal to moles over volume. Can I use the molarity of the chromium 3 chloride and the moles that I've calculated here to get the volume? be able to. The volume should equal the moles divided by the molarity. So I have 0.00042 moles and I have 0.0400 molarity. So the volume should be equal to, let's see, that's over 2, 0.0105 liters. Which is an answer. It's not asking me for any particular unit, so I can leave it as 0.10105 liters or 10.5 milliliters. All right. Is there a second part to this problem? How many grams of silver chloride are produced from part A? Okay. Stoichiometry. How much of one thing can be made from how much of another? I have a mole amount of silver nitrate that's reacting. That's as good as any to use. And now I want to know what? Moles of
Silver chloride.
silver chloride. So I have moles of silver chloride over moles of silver nitrate. That's what I already know. What's the relationship between those guys and where does it come from? Balanced equation. 3 to 3. Could I put 1 to 1 there? Wouldn't hurt. The reason I would put 3 to 3 is if I come back later to look at this problem and I have 1s there, I'm going to have a hard time figuring out where those 1s came from. So if I put 3 to 3, it's mathematically equivalent, but it lets me know that, oh yeah, they came from the balanced chemical equation. So this tells me that I have 0.00125 moles of silver chloride, and it wants grams of silver chloride. So silver is what? 107 or 108. Chlorine is about 35.5. So 143. 0.3. 143.3 grams for 1 mole. And then the correct math would take you to, I think I get 0.179 grams. Of the silver chloride. Questions? Is this something you think you could do on the next exam? Mixing stoichiometry and molarity.
More practice.
A little more practice, but doable. Understandable? Okay, we'll do another one on Wednesday when we get back. Take a look at an acid-base titration.